Hi, welcome back to Theory of Computer Science. This is COMS W3261, Summer B 2021 at Columbia University. And this is lecture 3.3. Title of this lecture is Regular Expressions are no more powerful or maybe I should say more expressive, but I'll stick with powerful for now, than NFAs. In particular, we're going to do a quick proof. We're going to show that given any regular expression, I can build an NFA that recognizes precisely the language the regular expression evaluates to. So if a language is regular, other way around, if a language is described by a regular expression, then it is regular. And the idea for why this is true is just, well, take any generic regular expression R. If we can build an NFA that recognizes the same language as R evaluates to, then we know if a language is described by a regular expression, it must be regular, right? Language described by regular expression, build an NFA. All languages recognized by NFAs are regular. We know that from earlier this lecture. So we get the result we want. In particular, we've defined R inductively. So we can build up our NFA inductively. So if you remember, right, we defined a regular expression formally in terms of 3 base cases, just very simple things that we can definitely write down an NFA to recognize, plus 3 inductive cases. That is, a regular expression can be the union of a regular expression with another. It can be the concatenation of a regular expression with another, or it can be the star of an existing regular expression. And if we can show that we can do that with NFAs, if we can mimic that inductive construction, then we can also create NFAs that recognize any generic regular expression. And this is where our proofs that the regular operations, that the regular languages are closed under the regular operations are going to come in handy. So here's our proof. Let's let R be a regular expression. By our definition, R takes one of 6 forms. We show how to build an NFA equivalent to each. What were our 6 forms? Well, first case was R is a single symbol in our alphabet. Then, well, the language var is just the language containing that single symbol. And the following NFA is equivalent. How do we recognize a single symbol within an NFA? Well, we just start and we accept precisely when we read in that symbol. So on the empty string, all branches of computation die. On a string that starts with any character besides A, the branch of computation dies. And finally, if we have a string that starts with A, but has any other character following, then all branches of computation die. So this is an NFA that recognizes precisely the language that contains only the symbol A and covers our first case. Our other two base cases are similarly simple. For instance, what if R is just the empty string? In this case, the language of R is the language containing the empty string. And the following NFA is equivalent. So you can imagine putting any string into the NFA below. If it's the empty string, we stop and accept. If it's any other string, all branches of computation die. So this NFA is indeed equivalent to the regular expression empty string. Our third case was that R was the empty language. So the language of R is the empty language, also written like this with two curly brackets and nothing inside. And the NFA that recognizes the empty language is my favorite NFA. It's an arrow pointing straight to the reject state. Do not go anywhere. Do not pass go. All branches of computation die immediately. So far, so good. If our regular expression is any one of these three simple things, then we can definitely build an NFA that recognizes the same language. The next thing are our more complicated cases. For instance, we said R is a regular expression if it's the union of two existing regular expressions. And it might seem tough to build an NFA that recognizes the union of any two generic regular expressions until you realize that we already did it. In part one of this lecture, we built a generic NFA that recognized the union of two regular languages. So if R1 and R2 are regular, which, they're regular expressions, and we've made this inductive claim that regular expressions correspond to regular languages, then R1 and R2, so we'll say, let's let N1 recognize R1, let machine N2 recognize R2. Well, here are our two NFAs. They've both got start states. They both have some intermediate states. They both have one or more accept states. Well, 0 or more accept states, I should say. It's always possible for an NFA to have no accept states. And we use precisely the construction that we used in our proof that the regular languages are closed under union. Under the assumption that we can make an NFA for R1 and R2, we can certainly make an NFA for N1 or for R1 union R2 with two epsilon edges, just like in our proof. And the idea is going to be the exact same for the other two cases. If our regular expression is R1 concatenated with R2, then we let N1 N2 be NFAs, recognizing R1 and R2, and we use our concatenation construction. That is, we want to make our end states from N1 no longer end states and add epsilon edges from all of the accept states of N1 to the start state of N2. That is, we're non-deterministically guessing where the two strings are concatenated, where to stop reading at R1 and start reading R2. Again, I'm not writing these cases out. I'm just drawing the pictures because the proofs are exactly the same as the proofs we did earlier for closure. And then the last one, R equals R1 star, where R1 is some other regular expression. Let N1 be an NFA, recognizing R1. We use our construction for star. That is, epsilon edges from every accept state back to the beginning, and another little bonus state with an epsilon edge to make sure we're capturing the empty string. And that is our entire proof. We're actually done, right? The reason we're done is because if you give me any regular expression, I can, by definition, recursively decompose it. It's the union of two things, which in turn might be the concatenation of two things or the union of two other things, all the way down to my base elements. And then following the proof I've just written out, I can then create NFAs for my base elements. And I can combine those NFAs using the three constructions I've just drawn all the way back up to create an NFA that recognizes the same language as my regular expression. So that is a complete proof that if a language is described by a regular expression, it's regular. Before we go today, I'm going to give you a concrete example of this process. So, concrete example of taking a specific regular expression and turning it into an NFA. This is a good thing to know how to do. And it also might make what we just did a little bit more concrete. So example, let's convert A union B star ABA to an NFA. Well, we can break this down into our tiniest pieces, our base elements. There's no empty strings or empty language as a part of this regular expression, so we just need NFAs for starters that recognize the language containing A and the language that contains B. So we know how to do this. That's an NFA that recognizes only A up top and an NFA that recognizes only B below. And now we just need to build up to our total expression. So we've got a union, we've got a star, and we've got some concatenated characters over there. Let's do the union first. So A union B. How do we recognize that with an NFA? Well, I'm going to start by drawing the two things we know, the two components. This is like N1 and N2 in the picture above. So whenever we have the union of two regular expressions, we can make an NFA that recognizes that union by adding an extra state, a new start state, that then has epsilon edges to the start of both of my other expressions. So that's an NFA that accepts A union B. Let's also do ABA. So I'm actually skipping a step because I'm doing two concatenations at once. So if you wanted to be really pedantic, you could take BA first or AB first, because it doesn't matter which of those two you evaluate first, and then concatenate that with whatever is left over. But we'll just say, you know, concatenation is pretty simple to extrapolate to a double concatenation. So we've got an A going on, we have B going on, and we've got another A over here. And how do we put together a concatenation? Well, it looks like we took the end states of the first NFAs in the concatenation and turned them into regular states. And then we connected the whole thing up with epsilon arrows. So those are no longer accept states. And there are epsilon arrows taking me from the end of my first NFA to the beginning of my second, the end of my second to the beginning of my third. Looking at this, you might realize, okay, in this particular case, the epsilon arrows aren't necessary. I can get just as far by writing down these four states, and this equivalent NFA. So I've just removed the epsilon arrows there to create a simplified but equivalent NFA. Great. Now we've got our A union B and our ABA. So we've got two more steps. Well, heck, let's just go for it. Let's do the entire expression. Let's do our A union B star ABA. So I'm going to start with our A union B. So we've got our added start state with our two epsilon edges. And then we have our little NFA recognizing A and our little NFA recognizing B. And that's the same as the one up there for A union B. I've just written it smaller, so we can fit everything in that we're going to do. What did we do for Kleene star? Well, for star, make it blue. We redirected our end states back to our start state with epsilon edges. Ooh, I'm precariously close to the line there, but I'm not crossing it. When I upload these notes, I'll try to add a margin. And we also add our extra accept state with an epsilon edge coming out of it, just to make sure we accept epsilon. So this chunk is now A union B star. And then finally, we need to just concatenate that with our NFA for ABA. So I'll draw that over here. So that is our NFA that accepts ABA. How do we do concatenation? Well, we remove, not that much. We make the end states of the first thing we're concatenating no longer end states, and we attach them by epsilon edges to the start state of our new thing. Ooh, don't want to forget that one. It's also an end state, also an accept state. So that is the complete NFA that recognizes the same language as our regular expression. And we built it up recursively, and we built it up following the procedure we outlined in the proof that you could do this in principle. So we've done it in principle, we've done it in practice, and hopefully now you could write a computer program to do this, to pick apart a regular expression and build an NFA. So that's all for this lecture. Thanks very much for watching. Let's see. We've got homework 2. Again, that's due Monday, 7/12/21 at 11:59 p.m. EST. And the readings again are CIPSR, end of 1.2. That's for, I think, the first part of this 3-part lecture, and 1.3 for the second 2 parts having to do with regular expressions. So thank you all so much for watching. If you have comments or questions, just email me or somebody in the course staff, or drop them in the Ed discussion. Thanks very much. Have a good one.